Welcome to section 4.3. This section is called Determining Statistical Significance. In section 4.1, we introduced the basic concept of a hypothesis test. What is it? What is it used for? All that good stuff. In section 4.2, we introduced the basic concept of a p-value. How do I estimate one with StatKey, and how do I interpret it once I have one? Now we're going to tie those two ideas together. So we're going to see how do I use a p-value to measure the strength of the evidence that I find in a hypothesis test. As always, we have a motivating question. Today's motivating question is, do more than 30% of people forget their to-go box at a restaurant? So the authors of your book were out at a restaurant and their server told them that 30% of the time that people request a to-go box, they leave it there. So that's the story behind this question. Suppose the restaurant wanted to look into this. They could take a random sample of 120 people who request a to-go box, and they could count how many of them forget to take it home. So there is what we've got. We want to do a hypothesis test. Any good hypothesis test starts with a set of hypotheses. So for us, that is a null of p equal to 0.3 and an alternative of p greater than 0.3, where p is the proportion of patrons at this particular restaurant, if we want to be specific, that forget their to-go box. So we'll pause for a second and we'll focus in on our hypotheses and say, where did this come from? Since I know it's probably been a few days or weeks since the last time you've tried to write a set of hypotheses. So first up, why is it the symbol p? Remember, only parameters are allowed to be in your hypotheses, and we're dealing with a proportion, so population proportion is p. It means it can't be a p hat because that would be our sample proportion. It can't be some symbol that you made up. It has to be a parameter, so we're choosing p here. And where did the alternative come from? We're going to look at the alternative first. Sometimes that can be helpful. So the alternative p greater than 0.3, that came from our motivating question. Do more than 30% forget the box? So p greater than 0.3. And then we've got a symbol, we've got a number. The null is easy. We know that the symbol and number need to match in both hypotheses and that the null can only have an equal sign in it, so the null becomes p equal to 0.3. And we're about to get a sample statistic, so before we do that, we need to know what to label it, because it is very important starting now to keep track of symbols. So the sample proportion, that's p hat. Now, when we find p hat, it's not going to equal 0.3 exactly, and that's okay. It does not need to. Our question is going to be whether or not it's different enough to conclude that the population parameter p is greater than 0.3. So here's a question to kind of get us started thinking about that. Which of the following sample statistics provides stronger evidence for the alternative hypothesis? A, p hat equal to 39 out of 120, or 0.325, or B, p hat equal to 51 out of 120, or 0.425. That's right, B. So 0.425 is farther away from 0.3 than 0.325, so it's giving us stronger evidence. And it turns out that that's actually pretty far out in the tail of the distribution, and it has a p-value of 0.002. You don't need to worry about where I came up with that right now. Just trust me, that's the p-value. So interpretation of that would be that it's very unlikely to have happened just by random chance. There's only a 0.2% chance of seeing this just by random chance if the null was true. But 0.325, that's actually in a likely part of the distribution. It's pretty much in the center, and it has a p-value of 0.283. That's not very unlikely, so it wouldn't be too unusual to see that just by random chance. our takeaway here is that a p-value of 0.002 is providing stronger evidence than a p-value of 0.283. Which leads us to a rule. The smaller the p-value, the stronger the evidence against the null. So now we've got a couple more questions. First up, which of the following p-values gives strongest evidence against the null? Is it A, 0.005, B, 0.1, C, 0.32, or D, 0.94? And feel free to use your fancy folding sheet of paper to vote, even though you're the only one who can see it. Makes it more fun. So, right, the answer is 0.005. And why? Well, because of our rule. The lower the p-value, the stronger the evidence, and that one is the lowest out of our 4 choices. Okay, new question and a new set of p-values. This time we're interested in knowing which of the following p-values gives the strongest evidence in favor of the alternative. A of 0.22, B of 0.45, C of 0.43, C of 0.03, sorry, or D of 0.71. So 0.22, 0.45, 0.03, or 0.71. Yep, that's right, 0.03. Why? Well, the lower the p-value, the stronger the evidence against the null, which means the stronger the evidence in favor of the alternative. So this was just another way to think about our initial question. So now we need to think about, well, how small is small enough? If we have 2 different numbers, we know which one is providing more evidence, but how do we know when we have enough evidence? And that's going to be related to this idea of a significance level. So here's a new vocab word and a new symbol. So our significance level, we usually denote it with an alpha. It's the threshold below which the p-value is deemed small enough to reject the null hypothesis. Apologies for the typo there. So formally, the decision-making process looks like this. If the p-value is less than alpha, we reject the null hypothesis. If the p-value is greater than alpha, we fail to reject the null hypothesis. So here's a fun little meme to help you remember that. Now note, these are the only 2 things that can happen. We can reject the null or we can fail to reject the null. It's the only 2 ways we say that. We never say we accept the null. More on that later. But we never say anything else either, right? These are the only 2 things we can say. So when I ask you what is the decision of the test, this is what I mean. This is what I'm looking for. Did you reject? Did you fail to reject? And why did you do that? So that's a common test question to be on the lookout for. And there are some common significance levels, 0.01, 0.05, 0.1. If a question doesn't specify, which your book likes to do, you're going to assume the significance level is 0.05. So that's the very common one. There's historical reasons behind that. You can look it up if you want to, but just go that 0.05 is common, so if we don't say what it is, just default to 0.05. Now, I said we never accept the null. We're going to do an example without elephants where we talk about why. So in our example, we've got the null hypothesis that X is an elephant versus the alternative that X is not an elephant. So what would you conclude if you got the following data? So we have 2 situations. First situation is we don't know what X is, but you're told that it has 4 legs. Well, that isn't enough to say it's not an elephant, right? It wouldn't be weird to hear that an elephant has 4 legs. They usually do, right? So there's a picture of an elephant, if you didn't know what an elephant was. And this isn't enough evidence to say that it has to be an elephant either, right? Plenty of other things have 4 legs. Dogs, for example, have 4 legs. So we can't say that it isn't an elephant, but we can't say that it is an elephant either. So all we can say is we fail to reject the idea that it's an elephant. What if instead we're told it walks on 2 legs? Well, this isn't impossible for an elephant, right? Trained circus elephants can do that, but it would be pretty unusual. Your typical elephant isn't going to be walking around on 2 legs. So, in this case, this is sufficient evidence to say it's not an elephant. So here we would reject the null hypothesis. So this example is an example of the fact that saying fail to reject the null is not the same thing as saying accept the null. So saying I can't say it isn't an elephant isn't the same thing as saying I can say it is an elephant, right? So knowing that something has 4 legs isn't enough to say it's an elephant. It's just not enough to say that it isn't. And that's a very important idea. So we do have to be very specific and careful with our wording here. Remember, the hard part of this class isn't the math. It is the wording, and that's going to be particularly important starting now. So speaking of words, we have another vocab word, and that is statistical significance. So significant is a special word in stats. It's when the p-value is less than alpha, we say something is statistically significant. Now, up until this point, we've talked about making the formal decision of the test, and we do it in stats language. But we need to translate it just back into context. That way, someone who isn't familiar with stats could still understand what decision we made. And we've got a little template for that, just like we had a template for interpreting confidence intervals. So if we fail to reject the null, our conclusion looks like this. At the alpha % level of significance, we do not have sufficient evidence to conclude blank. And then you insert the alternative. If we reject, then your conclusion states at the alpha % level of significance, you do have sufficient evidence to conclude, insert the alternative there. So, there's a little flexibility in the wording here. It doesn't need to look verbatim like mine. There are multiple ways to say this here. It's just important that you state your significance level, say whether or not you have evidence, and then of what. So there are 3 main pieces. You can state them in slightly different ways, but they need to be there. Most importantly, you need to state your significance level. We talked about how different levels of confidence, some of them are meaningful, a 90% confidence interval. Some of them are meaningless, a 100% confidence interval, or a 20% confidence interval. Same thing with statistical significance levels. So some significance levels are meaningful, some would be rather meaningless, so you do need to be transparent and state what level of significance you were dealing with. So now we'll go ahead and do an example, kind of putting chapter 4 all together, or at least sections 1 through 3 all together. And this example is about the relationship between the types of uniforms worn by professional hockey sports teams and the aggressiveness of the team. So in the study, they actually considered teams from the National Football League, so the NFL, and from the NHL. But for us, we're just going to focus on the NHL part of this. So what happened were participants with no knowledge of the teams were asked to rate the jerseys on characteristics such as, did they seem timid or aggressive? Did they seem nice or mean? Do you think they were good or bad? Those responses were all averaged together into something called a malevolence score, where a higher score means that your uniform looks more evil, basically. Then, to measure how aggressive a team was, the author used the amount of penalties. For the NFL, that was yards. For the NHL, it was minutes. They converted that to a z-score, averaged it for each team over the seasons from 1970 to 1986. And so now we've got a measure of malevolence, so that was their malevolence score, and we have a measure of perceived aggressiveness, which is penalties. So we want to know, is there a relationship between those 2 scores? Just as an example, this is the Hartford Whalers. This is a uniform that was perceived to be not very malevolent, so people didn't think this looked very evil. This is the Vancouver Canucks. They had a uniform that looked a little more menacing. So this is an example of how people were rating these uniforms. So our motivating question, like I hinted earlier, is there a correlation between the malevolence of a team's uniform and the perceived aggressiveness of the team? Now we need to form our hypotheses. And again, you could write these in words, but that's not what we want to do. We want to write them symbolically. So be careful on homework or on the test. If I ask you to write the hypotheses and I don't say write them in words, I mean write them symbolically. So our null is rho is equal to 0. Our alternative, rho is not equal to 0. And we've used a symbol, so we have to define it. Our symbol is rho, and it is the correlation between the malevolence of a team's uniform and the aggressiveness of the team. Where did this come from? Well, we're talking about correlation. Population correlation coefficient is rho, so that's where our symbol came from. If there was no correlation, rho would be 0, so that's our null, rho equal to 0. If there was correlation, it wouldn't be equal to 0. We didn't specify anything about the correlation. Do we think it's positive or negative? So that's why we've got the two-sided hypothesis here, where it's just not equal to 0. Next up, we need to find the statistic from the original sample. So here's a graph from StatKey. So this is a screenshot of some StatKey output. We see that the sample size was 21. There were 21 teams. R is 0.521 between malevolent score on the X and penalties in minutes on the Y, or the Z score for penalties anyway. So there's our sample statistic, R equal to 0.521. Again, it's an R because that's the symbol for the sample correlation coefficient. These aren't just symbols we're making up. We have to choose from our specific set of symbols that already exist. And in terms of how you do this on StatKey, I'll post a link to a video of someone explaining how you do a hypothesis test in StatKey, whether that's me or someone else. That's to be determined, but I'll link you to videos of how to use StatKey since we can't do that in class anymore. There we go. So we are taking 1,000 randomization samples and estimating the p-value. So we end up with this randomization dot plot of the correlation. So each dot on here represents a correlation coefficient from one of our 1,000 samples. And over there on the bottom, we see 0.521. That was the correlation coefficient from our original sample. And up top there, in the other box, we see that that corresponds to a p-value of 0.014, almost. So if this was a one-sided hypothesis test, we'd be done. But it's not, right? It was a not equal to, it's a two-tailed hypothesis test. So that means we need to do 2 times the number that we get from StatKey. So our p-value is actually 2 times 0.014, or 0.028. It's a small detail, but an important one to remember there. Okay, next up, we're making a decision. Remember, this is formal. We're doing it in statistic language. So we need to compare our p-value to alpha, but did we state an alpha? Nope. So what do we default to? Default to 0.05. So our p-value is less than alpha. We reject. So now we have a decision. We need to translate it back in context. So at the 5% level of significance, there was sufficient evidence to conclude that there is a correlation between the perceived malevolence of an NHL team's uniform and the aggressiveness of that team measured in penalty minutes.